Hello. Hi, everyone. I'll keep it short. So today's topic is discussing what are the various ways we want to do an interrupt moderation for whatever devices. Um, there is there's a different trend. Many users are ready to accept all new, great, and new features and everything new. And there is another extreme of users in the cloud who are moving from um, public to from private to public cloud, or from their software devices to hardware-based devices, while they still want to run 8 to 10 years old kernel and expect better performance. The users are either the tenants running in the cloud VM or the cloud operator himself who wants to have better utilization of the CPU that they are renting out. So the challenge that we faced is interrupt moderation. How do we do interrupt moderation for the virtio network devices? Um, the two main challenges that we face is one is one class of device which are VDPA device, very lightweight in nature, just accelerate the data path, and they have been mapped to the guest VM. This is one use case. The second one we found is the other class of users who prefer the virtio PCI device instead of VDPA. And these are based on the DPU of or Bluefield 3 that we come across. So how do we moderate the interrupts for these two? And the third part of that is how do we do it adaptively so that based on the dynamic workload, we can adjust to it. And what turns out is it's obviously a solved problem in Netdev community for many years. 2017, Tal Gilboa and Andy Gospodarek, they presented. Many drivers in Netdev now has it. It's a Netdev algorithm, dynamic interrupt moderation. So how do we do dynamic interrupt moderation for virtio? This is a step back to it to say, what's the scheme exist in virtio specification that can use the Netdev algorithm or not? The one scheme that is there in the spec, first, the background is why do we talk about spec is these are the guest VMs that's been deployed for last 8 years or 7 years who does not have any new fancy scheme, and we need to make it work and moderate the interrupt. So what the spec and the drivers have done is there is a feature called ring event index. In this scheme, what happens is the driver provides the ring indexes saying if you cross this index, then you notify me with an interrupt. Now, this scheme works well when the hypervisor and guest are sitting next to each other with a memory access latency of 10 nanoseconds because hypervisor can read the memory of the guest. When you have a PCI device, it can't be done in 10 nanoseconds. So we want to optimize and learn what to do there. There are several disadvantages of this scheme. It is still producer consumer index. It does not learn from the dynamic nature of the workload, which is throughput, packets, bytes per second, and the interrupt rate itself. So one can program the queue indices based on these three parameters and still achieve the dynamism. However, the drivers are not doing it. They are old. They just program the best effort queue indexes. If we implement this in the PCI device of either VDPA or the virtio PCI device, then it blocks the receive path because it needs to read this event queue indexes to learn periodically. And that blocks a certain receive path to learn about it. And the most worst thing that happened as part of this feature in virtio is if this feature is negotiated, then not just the interrupts are moderated or events, but the notification from the driver to device to post a new request is also moderated, which means that when the driver wants to post a packet, it will not notify to the device that I have posted a packet. The device is expected to constantly poll for it that to happen. This can work for small number of count, but it does not scale when we have thousands of queues across hundreds of VMs. So this was hard to implement for VDPA and virtio device. The second key scheme that happened is okay, let's improve. The improvement happened is like any other modern device, Broadcom, Mellanox, Intel, all several of them. Let's have a per queue control so that we can moderate the interrupt rate based on the time as well as packets. And then the Netdev library can control how frequently it can modify these values. Now, this is, I think, the most modern scheme that we have so far. Here also we hit a second issue that the spec is new, has all the features, but the driver is not using it because driver is old. Some drivers have started using it, but they do only for the receive queues, but it doesn't do for the TX queue. Now, TX where you want to moderate the interrupts, but there is no effect on the latency because the TX queue depth is can be very easily adjusted based on the polling mode. So this scheme was okay, but not fulfilling the user's use case that they want to reduce the interrupt rate. The third thing that happened is that the driver that got developed was using the RTNL lock while modifying for all the queues. Means it affected all other devices in the same VM while modifying and issuing the command to the device. So for us, basically the challenge is have a old guest VMs, new PCI device, don't negotiate the event index, don't negotiate the new feature, and still achieve the interrupt rate. So that brings us to solve using a standard Netdev of Linux. How do we do it? So we solved it in two different ways. I'll come to the first VDPA part. I'll be honest here, I don't have a number for the VDPA device. I'm going to show the performance number with the virtio PCI device. But the design is more or less same. So until now, the Netdev library is always used by the net device driver who is operating the queue. And here what we did in the solution is the queues are in the guest VM, the TX queues and RX queues. They are exposed using a VDPA device here. So VM1 has a TX and RX queue. It comes through a ConnectX VDPA device. And this VDPA device gets the statistics from the actual device. We wanted to keep the device as stateless as possible. So what we do is the VDPA device registers with the Netdev library, and that library does all the calculations of what's the throughput, what's the interrupt rate, what's the bytes per second, and this library is being fed by the device about what's the interrupt rate that it is serving. So this way we exploit or use the Netdev library in the hypervisor to moderate the interrupts of the VM. And this way, so there are two paths. One is the interrupt configuration part, and one is the statistics gathering part. So the stateless hardware feeds in this data, and it receives the command from the MLX5 VDPA driver to moderate the interrupt. This was one scheme that we deployed. So it kind of matches the VDPA's kernel model, where the hypervisor is involved in taking the major control part decisions. So in this case, the guest VMs are unmodified. The device has been slightly modified to measure the interrupt rate and other statistics. The core logic still remains in the Linux kernel Netdev, so one can monitor and have better visibility from the hypervisor. Now that brings us to our second class of users, where uh, um, the second class of users is a virtio PCI device, where there is no hypervisor involved because these devices are passed through. I don't have a diagram here. Uh, do I? Okay, it is. So in this mode, what we see on the left side is a VM1, which has a virtio net device as a pass-through device. And now there is no hypervisor library of netdim involved here. In this case, what do we do? What we do is we offloaded the netdim algorithm to the DPU because DPU is a programmable device that has a processing power at a very cheap power footprint. There are many cores who is processing it, and the calculations done here are most U32 or U64 math. So it was easily doable for the virtio PCI device. So what we did is we offloaded this into the DPU, and that enabled um, more wider use cases. For example, there are many bare metal systems who are still using 7.x or early 8x Linux kernel, 8x Red Hat or other OS with a slightly older kernels. I don't know, slightly or more, 4, 5 series kernel that does not have any of the support. In this case, we put the netdim algorithm logic very similar to what Linux had, with slightly changes onto the DPU. And with that, we achieve the performance numbers that we see. We ran the test with a slightly smaller configuration with classic hyper micro benchmark. We used 2 RxQs for each device, and the Q depth is set to 1K, and the MTU is set to 9K. Why 9K is what our users was using in their setup. We want to be as close to their setup. And with this, our interrupt rate, previously for each queue, we were serving 44,000 interrupts. Now that moved to 15,000 interrupts. Throughput largely remained the same. Here the hardware GRO was not possible, so we obviously kept it disabled. Many of the workload at a high scale, the total number of GRO streams may not be feasible from the hardware. So to keep it as close to the real workload, there's no hardware GRO here. The CPU utilization had a slight gain, around 9%, from 62 to 53% on each CPU. So all the numbers are per queue per CPU here. And this was good, but we hit another problem. The moment we enable the netdim algorithm, if you remember, there is a left and the right side. The leftmost side is minimum it can go to 2 microseconds, which means that even if you get a packet, you won't get interrupted until 2 microseconds has passed. That affects our latency. So what do we do for the latency? Turn out again the DPU and processing of the cheap DPU power was useful. So what we did is we started learning from the heuristics. The netdim algorithm already takes three parameters in consideration: packets per second, bytes per second, and the generated interrupts. These are the 3 parameters that exist. What we added to that is to learn how can we improve the latency for short messages, TCP/ACK messages. So there are for DPU, there is a packet metadata is available for several of these packets. So we monitor the packets metadata, that are the TCP/ACK packets, TCP/ACK only, or what's in every batch being processed of the packet, what's the ratio of packet bytes to the packet count. And when it hits certain threshold, then we learn that, okay, there are too many TCP/ACK packets in a stream. We got to we got to respond fast and raise the interrupt. In the second case, when we saw that the messages are very small in nature for a given batch of packets, we raise the interrupt early, and that way we sort of short circuit the 2 microsecond time. And that brings us back to the same latency that we previously enjoyed without the Netdev. That's pretty much the gist of it. It's still not very accurate in the nature because the generated interrupts are sort of measured from the device side. In the real world, the interrupts are actually measured by the current NetDim from the guest VM or from the bare metal. But it's a reasonable approximation that sort of works to reach the desired throughput and gain the good latency. So that's a short talk. With that, I'd like to summarize is 3 points. The VDPA solution sort of works for a low scale number of queues or in the range of hundreds because the hypervisor is involved in monitoring the packet rate, interrupt rate. There is a constant traffic in the VDPA case. I think I skipped that, but you see this diagram. There is a constant communication that happening from the hypervisor to device to basically monitor the packet and interrupt rate. So at a 10 millisecond frequency we monitor, it's around 100 more interrupts per second right from the hypervisor. So that has a hard limit on scaling of how many number of commands can be executed by the device. And that limitation we sort of overcome with the DPUs, but then there is no hypervisor communication at all. It's a pass-through device and you get the best CPU utilization on the hypervisor, calculation-wise and the communication jitter-wise also. So for high scale, we find that DPU mode where the NetDim offload on the device is more useful. Latency enhancements wise, we don't see a good gain yet from the TCP. I think we are still early in our performance measurements. But the latency gain with message rate and the message size analysis was more helpful. That's it. Thank you. Questions?
Yeah. So basically, you're not notifications are not affected at all, right?
Yes, that's a good point. The driver notifications are not affected at all.
So, and you're not using F index at all in these kernels. You don't have. So how do you make sure that the
F index feature is there?
Yeah.
But the device does not offer it. Since the device doesn't offer, driver don't negotiate and they don't moderate.
Driver, do you? So every time you add something to the ring, you interrupt the what?
Yes, the driver interrupts the device, but it's really not an interrupt because these are MMIO memory writes. So device is built to handle incoming memory writes.
I think if I'm remembering correctly, there used to be in the config space, there used to be another field. I think there was one for the notification and one for the event. Like the driver, before it stops reading the ring, it can set, next time you add something, please notify me.
The feature flag is just one. The notify data is that?
No, so I'm sorry, interrupt me. Basically, when the driver stops reading the ring, when it thinks that it is empty, you can say, oh, when it tells the device by setting a field in the config space, saying, next time you add something to the ring, please interrupt me.
So it's not in the config space, but it is a per queue, and it's at the end of the queue. So every queue has, if you consider a split queue of the virtio, then you have a available index area.
Yeah, there's a well and used, but
yes, and the sad part is that it's been placed at two extremes of the queue.
Oh, okay.
So when you place the available index, you You have to do 2 DMAs from the device side uh, to learn about the index, where to.
No, but that is to find out the like next entry in the ring. But that is when the CPU, the driver CPU, is already active and basically looking at the ring, right? But to wake up the driver if it is basically interrupted, there's another like before event index. I think there was like an older way of doing it, where in this config space you have for each ring there's like a bit or something that basically you set and specify the device next time interrupt me.
I'm not familiar with. I'm sure it's not there in the config space. Maybe Eugenio, you have something to add?
Hello. Okay. So yeah, we have, apart from the from the event index, we have a flag. We have a flag that indicates if you want the other side to notify you, parts from the event index.
I mean, the device to notify to the driver.
Yeah, both sides. At the device one in the user index and the reverse in the avail index. Yeah, it's from the beginning. You don't need any feature flag for.
It's always there. It's there in 1.0 spec, but it was there even before 1.0, I think.
I think it's from the beginning.
But it's the same feature bit. The moment you enable, it applies both ways. Once the feature is negotiated, driver will also moderate it. That's the problem. The flag is kind of indication to either ignore or truly believe in it. But it's kind of a racy, because by the time you read it, it might got updated. So as long as if they both hypervisor and guest are in the same memory range, it's doable. And they are apart on a PCI bus, it's hard.
Yeah, I think that flag, kind of notify me whenever that you reach to some index come from the 1.0, so it's still there for 1.0, and but the problem is that is on the feature, not actually on the configuration space. So whenever that the device had to get that information into load that information from the host memory. So that's why it has to get into store the entire pipeline of the device. I guess one of the possible enhancements that possibly we can measure, try to use another to have that either through a new feature that get that added into the configuration space. So possibly some device which is capable of doing that kind of register access will be able to use that configuration space to access the index. So that will be able for the driver to pass it down to the device. So, but the problem is that how performant that it can be. That would be a question.
Okay. A quick one? Yeah. Okay. So when you run netdim in the DPU, you just not advertise the coalescing flag? Yeah.
Correct. We don't advertise both the flag. One is the event index and the other wiki. Both.
All right. I think we'll wrap it up here. Thank you.
Thank you, everyone.